Okay, so thank you very much. Hello, everybody. Of course, first of all, I would like to thank the organizers for inviting me at this fantastic workshop, conference. My talk would be strongly related to the previous one on Many-Body Localizations, and is based on a work done in collaboration with Marco Schirò, who's also in Paris, and I apologize for the fact that there will be no replica at all in my presentation. So I will be very, very fast on the introductions, since you have already heard from Antonello and Marcus that isolated interacting quantum system can actually fail to thermalize if they are subjected to strong enough disorder, even at finite energy density, and this phenomenon is known as Many-Body Localization, and it corresponds to a totally novel quantum out of equilibrium dynamical phase transition, which is essentially due to Anderson localization of the many-body wave function in the Hilbert space, and this localization of the many-body wave function has several remarkable and spectacular consequences, which have already been mentioned by Antonello and Marcus, most of them, and this MBL phase has been observed in several 1D disordered quantum models, both in numerical simulations and in experiments. Okay, so in the latest years, a huge amount of work have been done on this subject, and especially in establishing the properties and the existence of this MBL phase, yet much less is known about the nature of the transition from the MBL phase to the metallic one, and there are still a lot of open questions on this problem. And while it is commonly accepted that the metallic sufficiently weak disorder or sufficiently strong interaction, the eigenstates become fully ergodic and transport fully diffusive, just like in clean non-integrable systems, it was proposed that actually diffusivity and ergodicity break down before the MBL transition. This opened the possibility of the existence of a broad intermediate region where wave function might be delocalized but non-ergodic and transport highly heterogeneous. And actually the interest on this side, on the delocalized side of the transition, only started very recently, only basically a couple of years ago, when several, maybe 3-4 years ago, when several observations, independent observation, pointed out that actually the properties of this bad metal phase are in fact very unusual, and in particular in a broad range of parameters preceding this MBL transition, there is, so transport becomes sub-diffusive, and relaxation, out of equilibrium relaxation is anomalously slow and described by power laws with exponents that gradually evolve in this bad metal region and approach zero, say, at the transition, and these plots are just examples taken from 4 different papers which studied different 1D disordered models with several numerical techniques and also with experiment with atomic gases. Okay, so appealing phenomenological explanations of this behavior has been provided or proposed in terms of Griffiths effect. Basically, this means that low frequency response in this regime, this metal regime, is dominated by rare regions. So a little bit more precisely, the idea is that a system close to the MBL transition is made by a patchwork of locally thermal and locally insulating regions, and these regions in 1D affect dramatically the dynamics and the transport, since quantum excitations have to go through broadly distributed effective barriers, which produce low dynamics, slow power law relaxation, sub-diffusive dynamics, and anomalous spectral correlations. So the first descriptions of Griffith effects of the bad metal sub-diffusive phase in terms of Griffith effects was proposed in terms of purely effective classical models, like classical resistor capacitor models, very similar in spirit to the trap model, Jean-Philippe trap model for glassy dynamics. And then later, this Griffith effect have been studied within the framework of several strong disorder renormalization, phenomenological renormalization group approximations, trying to describe the asymptotic critical behavior of the many-body localization transitions. And these several propositions, these several schemes, the first work are just numerically implemented RG strong disorder schemes that are all based on the same idea, which is that close enough to the MBL transition, one can introduce coarse-grained effective models which describe the formation of collective many-body resonances which destroy the insulating phase. And these models are basically made of resonant locally thermal and locally insulating clusters, which are built on random matrices and are described by a minimal set of parameters, say the local bandwidth, typical matrix element between two levels, and so on. And then on a different front, in the latest years, it has been put forward by Marcus and collaborators that the thermalization transition coming from the insulating phase might be driven by ergodic bubbles, which are thermal inclusions of weak disorders or region of weak disorder, which naturally arise in the insulating phase and then can trigger thermalization avalanches. And the latest RG, simplified RG studies of the first months actually showed that this avalanche, including this avalanche mechanism with a natural choice of the scaling parameters, naturally lead to a Kosterlitz-Thouless-like kind of criticality for the MBL transition. However, so all these approaches are based on the idea that the MBL transition is universal and thermal, so it can be described by effective classical-like statistical mechanics models. However, all this is purely phenomenological. It's not mostly all that is purely phenomenological. It's not based on any microscopic description. So the aim of our work is to have a tractable toy model, which on one end is able to reproduce the critical behavior of the phenomenological RGs, and on the other hand, it retains a quantum mechanical nature, so allowing one to study, for instance, the effect of Griffith effect in quantum dynamics. So this is our toy model that we propose, which is described by this Hamiltonian. Sorry, the pointer doesn't work very well. This Hamiltonian, and it's illustrated by this drawing. So the first two terms of this Hamiltonian are just M copies, M identical copies of, or replicas, if you want, of a 1D Anderson insulator along these horizontal red lines. So the copies are labeled by this index P, which goes from 1 to M, while the index I just labels the position along the X direction. And so at a given position I of this chain of layers, all the sites that belong to a given layers are coupled by the last term of this Hamiltonian, which just corresponds to hopping on a sparse random matrix. And in particular, we'll take the connectivity matrix of a random regular graph that, as you have heard in the previous days, is just a sparse random matrix which has locally a tree-like structure, but has large loops and no boundaries. So the epsilon I here are just random on-site energies taken as usual from independently distributed from a box distribution of width W. T is the hopping rate in the X direction, which allows a particle to jump from one layer to the next. Gamma is the intra-layer hopping, which connects, say, two sites P and Q on the layer I, which are connected by an edge of the random regular graph. And it's important to say at this point that if we take on each layer different realization of the random regular graph in such a way that if an edge is present on a given layer in the large M limit, with very high probability there will be no such edge in the other layers, so the whole lattice can still be seen as a tree-like structure, although it is anisotropic in one direction. Okay, so this is the matrix representation of the same Hamiltonian as before. It's just composed of L square blocks of M times M matrices. The diagonal blocks are just minus gamma times the connectivity matrix of the random regular graph on the layer I, which is different on each layer, shifted by the random energies epsilon I on each layer. And the off-diagonal blocks are just minus T times the identity matrix. So if one wants to make a connection with the effective coarse-grained models introduced in the context of the strong disorder RG, one might imagine that each layer I can be thought as a very pictorial representation of coarse-grained block, or say of a certain number, small n of sides of an interacting model, and the random regular graph on each layer provides a very schematic pictorial view of the Hilbert space of these local degrees of freedom. And so within this interpretation, the local degrees of freedom of the toy model should be thought as quasi-particle many-body quantum excitations in some of the local degrees of freedom in some local basis, and so T plays the role of sort of entanglement rate between energy levels of this quasi-particle excitation on neighboring blocks. So it has been shown by even rigorously that in absence of disorder, the random regular graph belongs to universality graph class of the GOE matrices, so with fully delocalized eigenvectors and Wigner-Dyson statistics. So the gamma term basically is a coupling with local GOE perturbation, so basically a local bath. So it's a term that mimics the interaction because it allows, in principle, the system to delocalize. And so this model, on one end, as you can see, it's just, if you know how the coarse-grained effective models of the strong disorder RG were built, it's just like a microscopic implementation of this model on the similar, it can be thought as a kind of simplified microscopic implementation of these effective coarse-grained models. And on the other hand, it's a model that allows to study how an Anderson insulator can react to the coupling with the thermal bath, so it can lead to the picture of quantum avalanches. Okay, so when this coupling with the local GOE perturbation is increased, the model I will show, as I will show you in the following, undergoes a transition to from an insulating phase to a conducting one. The simplest way to understand the mechanism for this transition is just provided by the locator expansion. So for gamma equal to 0, you just have unperturbed 1D Anderson insulator. The green function between 2 points just can be expanded as usual as a sum over all possible paths which connect these 2 points, and the weight of each path decreases exponentially with the distance, so only the forward scattering paths contribute to the sum. But now, when gamma is turned on, now a huge number of new paths are generated because a particle can jump several steps within the random regular graph for a given layer before jumping to the next. So we have to replace this expression by this one, and just by comparing these two, we realize that the effect of gamma is to renormalize the local energies, epsilon I, in this way, epsilon L, and this can clearly enhance resonances because it can generate, in principle, arbitrarily large terms in the sum on the sites where the energy is sufficiently small, and in particular smaller than k times gamma. And so it's natural to expect that delocalization in this toy model can be actually occurs when on a chain of length L, the probability of finding at least one of such resonances becomes of order 1. And so delocalization is likely to be driven by few rare resonances that are there for some specific realization of the disorder. Okay, so the model is a model for non-interacting particle on a tree-like, although anisotropic structure, so it can be solved exactly just by writing quasi-exact self-consistent relations for the green functions. And in order to study transition, one can just expand this green function in power gamma square and ask if this perturbative expansion converges or not, and when it doesn't, it means that a stable non-singular probability distribution of the imaginary part of the green function is generated just by the effect of gamma. And so just by doing this, here one can study when a chain of length L is localized or not, and this is given in this plot. This is the probability that a chain of length L is localized as a function of gamma for different values of the disorder and different system sizes, which correspond to different symbols. So this plot just tells us that the probability that a chain is localized decreases exponentially with the length of the chain and with gamma, and the data corresponds to different system sizes just collapse very nicely one on top of the other when gamma is multiplied by L. So basically this means that the probability that a chain of length L is localized is given by this expression, and exponentially distributed localized segments is precisely one of the distinctive features of Griffith phases. And this expression also tells us that the characteristic scale for localization to a coarse, which was also supported by the locator expansion, the argument based on the locator expansion, is of the order of 1 over the length of the chain. So in order to draw the phase diagram of the model, we introduce this new control parameter, which is the x-exponent phi, which basically tells us how fast this gamma coupling with the GOE perturbation decreases with the length of the chain. So in the limit of infinite chains, we are on this axis here. So for phi smaller than 1, with probability 1, the chain is conducting. For phi larger than 1, with probability 1, the chain is insulating. Yet at finite L, a broad intermediate region emerges where arbitrarily large, meaning on the sides of the chain, conducting and insulating segment coexists. And in particular, these lines here are just the probability that the chain is localized is smaller than delta on the conducting side and larger than 1 minus delta on the delocalized side, with delta very small, say 10 to the minus 2, 3, and 4 here. So all these lines shrink to the critical point in the thermodynamic limit, yet at the critical point, one can still fine-tune the value of P loc between 0 and 1 just by changing this value of this rescaled gamma hat. Okay, so now we start focusing on the properties of this intermediate region, which is the one which interests us. So we set phi equal to 1. Here we're in the middle, and we take beginning L large. We first study statistics of dissipation propagation inside these chains. So in order to do this, we put a source of dissipation at the origin. This is for periodic boundary conditions. And we look at how this dissipation propagates through the chains. These are the parameters used here. Different colors correspond to different realization of the disorder, but for the same parameters. And for this choice of the parameter, P loc is about 1/2. So half of the samples are localized, and the other half is conducting. These are the localized samples. So for those samples, this is the imaginary part of the green function as a function of the position along the chain. It just goes down exponentially, as in standard 1D Anderson insulator, over a typical localization length, psi typical, which is the same for all the samples, and until reaching a very small value in the middle, and then just comes up back due to the boundary conditions. And so basically, this tells us that for those insulating samples, the effect of turning on gamma is purely perturbatively small, only perturbatively small, because this psi typical turned out to be just a little bit larger than the bare one, the psi naught of the gamma equal to 0 Anderson insulator. Instead, the other ones are the conducting samples, which are clearly made of patchworks of localized segments separated by rare resonances. So for instance, take this red curve here. We can clearly identify three insulating blocks, which are separated by 2 resonances. So on the insulating blocks, mg just goes down exponentially, just as the insulating samples with over the same localization length psi typical. But then when a resonance is found, mg comes back up to values of order 1. Okay, so this is completely different from what happens at the standard Anderson critical point. It's a totally novel mechanism for understanding localization, and actually is indeed very similar. It's basically the localization E in this toy model is due to this avalanche mechanism, because we see that sparse network of few resonances, rare resonances, is enough to produce a conducting state. You're putting the resonance regions in by hand, and then looking at the effects. Basically, you can the model microscopically is defined like that, but basically, if you look at my argument is that if you look at the locator expansion, for some realization of the disorder, you can have with some probability resonances, and this one is enough to make explode the sum. So basically, it's a model built to have this effect. Okay, so we study the implications of this anomalous delocalization tradition on correlation functions, which are just green function at distance 6, which actually are proportional, say, to the probability that I take a particle at a certain point at time 0, and I look at the probability that a particle is at distance 6 after infinite time. And so since one can expect that these correlation functions are dominated by rare regions, we measure both average and typical ones. So these are the results shown in this plot. For the same values of the parameters of before, same different several values of the system size, and now we average over several iterations of the disorder. So typical correlation are this dashed blue line here, just show the usual exponential decay with the distance. And they do not depend on the system size, and as I said before, psi typical extracted from, which is just the slope of this straight line, is just proportional to psi naught. The bare Anderson localization length in absence of gamma is just finite everywhere. Instead, average correlation behave completely different. They decay much slower. They are well fitted by stretched exponentials. And these features have been already observed numerically in the resolution of the RG schemes, and have been interpreted in terms of a fractal network of sparse thermal inclusions or resonances. And actually, so this plot here shows how this fractal dimension, df of the stretch exponential extracted from the fit, behaves with the system length of the chain. And actually, we see that it's very slowly but systematically decreases with the system size, which was also what was observed in the numerical resolution of the RGs. And the other striking feature is that this correlation function increase actually. They do depend strongly on the system size. They become stronger and stronger when the length of the chain is increased. So this can be understood just by invoking a broad distribution of localization length. So basically the idea is that you pick 2 points at random. Typical correlation are just exponentially small because typically there is no resonance, just standard Anderson insulator, just renormalize perturbative a little bit psi naught. Then average correlation is instead dominated by few rare pair of points on which correlation can become arbitrarily large. So they dominate the average because of the tails of the distribution. Okay, so all that is fully consistent with the KT scenario recently proposed in these papers, in this very recent paper for the MBL transition. Okay, so now just in the last 5 minutes, I don't know, I would like just to show you the implications of these behaviors on the quantum dynamics of the system. So we take an initial state which corresponds to a particle sitting on a site IP, with P chosen just at random between 1 and M, so at random in a given layer, and I in such a way that the energy on the layer is very small, close to 0, so it's a very high temperature initial state, and we let it evolve. And this is the wave function at time t, just written in terms generically of the eigenvector, eigenvalues of the Hamiltonian, and we measure observables that have been studied in the literature to characterize the properties of this bed metal phase, and in particular the return probability, just which in a many-body system would be the analogous of the correlation function. Basically, it's the probability that the particle after time t is found at the same layer where it started. In the same way, we can define the mean square displacement, which is the average distance squared traveled by the excitation between 0 and t, defined this way. And this quantity, we computed them from exact diagonalization. And from exact diagonalization, we can also compute the AC optical conductivity. This is just written in linear response in a lemma representation and limit of very high temperature, where this current operator J here is just found by continuity equation in x direction. We're only interested in the x direction. Okay, so now I show you the results found by exact diagonalization. So here the length of the chain is 36, and disorder now is largely 16 compared to the previous plots, just because we want that the bare localization length is much smaller of the length of the chain. And since with exact diagonalization we are obliged to study small system, we have to increase the value of the disorder. Otherwise the parameters are more or less the same as before, and in principle different colors here correspond to different values of the coupling with the GOE matrices across this intermediate phase. So actually they correspond to these blue points here on this phase diagram. So 1 over L is 1 over 36, and the different colors correspond to this point, different values of this exponent phi really across the intermediate region. Okay, so what we see is the following. So a very short time, the mean square displacement grows ballistically. So this black dashed line is the result for the pure Anderson insulator, standard insulator, gamma equal to 0, used just to benchmark the result to interpret them. So short time, the mean square displacement grows ballistically until the wave packet spreads over xi naught, the bare Anderson localization length, and the return probability decreases exponentially until it reaches the value of the inverse participation ratio of unperturbed Anderson localized wave function in the middle of the band. And then at later times, for t larger than xi naught, clearly a slow dynamical regime sets in, where the mean square displacement grows sub-diffusively, and the return probability decreases with a power law in time, and concomitantly the AC optical conductivity at low frequency vanishes with an anomalous exponent. And so this plot shows you how these exponents, beta, beta prime, and alpha, vary along inside the intermediate region, and they also show that they nicely within our numerical accuracy, satisfy the expected scaling relations also observed in the case of MBL. So all in all, this at least pictorially, this behavior is strikingly similar to the one that I showed you before at the beginning, which were found in the numerically in experiments, in recent numerical experiments on the bed metal region of the approaching the many-body localization. And so this is, I just finished here, just want to sum up. So basically, I just presented a toy model analytically solvable for Griffiths effect and anomalous transport for MBL, which on the one hand is built as a microscopic description, like a microscopic implementation of the coarse-grained effective models introduced in the context of DRG, and still it retains full quantum mechanical nature, and it is basically able to reproduce most of the key features which have been discussed in the context of this sub-diffusive bed metal region, and then so it can be thought as a first step to bridge the gap between microscopic physics and long wavelength effective behavior of DRG. And just here we have some possible direction for future work. I don't know if I still have time. Yes? How much time do I have?
1 minute.
1 minute, fair, fine. So one thing would be really to be able to determine precisely the critical behavior of the model and to show that it's really KT-like or not. Of course, for a KT transition, you expect, and this is what we observe, huge finite size effect. So one should think to clever ways of doing that. And another, maybe the most important thing is that actually this anomalous bed metal-like behavior sub-diffusive region has been also found in systems with quasi-periodic disorder in 1D or disordered system in 2D. So where in this case, on general grounds, you expect the Griffiths effect should be only milder or subdominant if the disorder is correlated or the dimension is larger than 1. So it is natural to look for other possible mechanism that might complement the Griffith picture beyond the case of 1D uncorrelated disorder. And some work we did with Giulio in this direction. But basically, this means that one really needs to understand the relationship between rare Griffith regions in real space and multifractality of wave function in Hilbert phase, which is of course a very interesting problem, but really also a very hard one. And another promising direction in this respect would be to repeat this analysis in the case, instead of taking a IID disorder, uncorrelated, the idea would be to study the critical property of the model in the case of a quasi-periodic potential and see what changes. And on that, I just thank you all for your attention.
So, thank you. So, yes?
Okay, so on a few slides back, you have these power laws in omega that you have.
Yeah.
Those you think are asymptotically right in these regimes, or that's still a crossover?
I believe that they are, I mean, the model is basically built to have this power law. So I believe that they are true. In the diagonalization, of course, there will be a crossover due to the smallest level that you can, I mean, at a certain edge on the diagonalization, you can go to a small scale. So, I mean, I think one could solve the model by Keldysh and show that you really have these power laws. It's a little bit of effort for a non-interacting system, so we decided not to do this, but I think in principle it's doable.
Okay. Any other question?
Can you comment on this KT-like? I mean, what is Kosterlitz-Thouless and what do you exactly mean by it?
Yeah, I mean, sorry, I had the slide on that. If we can look, voila, that's what I mean. So, okay, so this is average value of the imaginary part of G and typical value of G for two, this is for two different sizes, two different length chain, 2 to the 8 and 2 to the 11, as a function of gamma hat, this rescale gamma, and for two different samples. So blue and light blue are average and typical, and red and orange are average and typical, and the typical is rescaled by a factor L. Okay, so before, take the blue. Before you have no resonances, so the system just behaves as a standard Anderson insulator. Then the first resonance appears. Mg average becomes of order 1 because the value of the average dominated by just one resonance is enough to have value of order 1. The typical value is exponentially small in the system size, but has the same singularity, square root singularity as Anderson. But then order 1 gamma later, a second resonance appears, so you have a cusp on Mg and then a jump in average Mg, in typical, which is also exponentially small. Okay? And then and so on and so forth. And this, in the limit of infinite chains, this is gamma hat. So in the limit of infinite chains, this whole cusp, sequence of cusps, they all merge to a point. And so they can change the square root singularity in an exponential one. That's what I would like to be able to show, but of course, one needs to go in the limit of infinite L. So for me, a resonance is the equivalent, even though it's not a topological excitation, so it's equivalent of one vortex, and then two vortices, and so on. And this scaling of the parameters allows us to zoom on the critical point, so in the region where few order 1 vortices are there. But the true transition is due to proliferation of vortices. So in the limit of infinite chain, these 1, 2, 3, 4 vortices all squeeze in a point. And this can give rise to KT. But it's not so simple to analyze.
Okay. So any other question? No? So thank the speaker again.